Okay, let's start the lecture. So I'm gonna do a quick review at here, and then we'll go into the topic surface integral for flux. Okay. Again, I'll start from the review on the curl. Okay, this is the formula for curl if we have a vector field in 3D space. So the vector field is a function of x, y, z. Then curl, the computation is, straightforward. Just do a cross product, del cross f, and the formula is this here. Okay, so you will have the formula. So in terms of computation, everybody should be able to calculate del cross f. Okay, yeah. If the vector field is a 2D, so it's just a function of x and y. There's no z component at here. Then this formula will become simplified. It's just having one k component, k hat component at here. Okay? Yeah. So basically means if you have a planar vector field in the xy plane, then the curl of that vector field will give you a vector which is in the k hat direction. Okay? Yeah. Any questions in terms of computation in here? Is that good? So, and then the hard part for that particular lecture is what's the meaning behind the curl f or del cross f, right? So that's the one often in time you probably struggle. But at least you should remember this simple fact about the curl f. Okay. So here is the definition of a curl f here. So curl f dot n hat equal to this limit at here. So in this definition, the n hat, basically what the n hat represents is a uninormal vector. So if you have a curve C, in the 3D space, and the curve C includes certain kind of a region. So curve C includes certain kind of region delta A, and we express the region using the vector delta A vector. The orientation basically is given by its uninormal vector n hat. So the n hat is normal to this delta A vector. Okay? The magnitude of this delta A vector is the area enclosed by the C. Right? So that's the relationship between those symbols at here. And then the definition here is the curl f dot n hat will equal to the circulation over the area, and then let the area approach to 0. So this is a density concept. And this integral here, we know that this is a line integral. So line integral, or what we call it, this is a circulation around curve C. So circulation around curve C over its enclosed area delta A, so we get basic so-called circulation density here. Okay? So curl f dot n hat equal to the circulation density. If a purely based on a dot product, this means the projection of this curl f vector in the direction of n hat. Right? This is what it means. So purely meaning from the definition is projection of this curl vector f, or the basically del cross f, the curl, in the n hat direction, give you the circulation density at that point P. So that's the definition here. Okay. So the immediate observation based on the definition is, so apparently you have, right, you basically, what you have here is, you're letting the delta area go to 0. So the circulation density or the curl f calculation here is with respect to a point concept. So this is why in the last lecture I mentioned this, the curl describes the so-called microscopic circulation. So very, very tiny, we're at the point, microscopic circulation, right? Yeah. And the other thing is, if this is n hat, if this is a curl f here, and then curl f dot n hat, right? Curl f dot n hat. The projection of this in the n hat direction give you the circulation density. So apparently, the circulation density will be maximum if what? If the n hat is in the same direction as curl F. Does that make sense, right? So those are purely based on the definition here, okay? And the maximum value is basically the magnitude of this one here, right? Dot product. Okay, so maximum circulation density is the magnitude of the curl at here. Okay, yeah. And what information does the curl give us? Give us the microscopic circulation at a certain point. Okay, yeah. Those are basically the meaning here. And in the previous lecture, I give you an example. This is the flow of a river. And this is the vector field generated by this function here. If I do the cross product or the curl of this vector field, and I end up with this quantity. Apparently, you see, there is, at the different y value, there's non-zero. So which means this is non-zero. At the different y value, you have a different kind of a circulation going on there, right? Yeah. So in this particular case, what it means is you put a stick at here or here. There's going to be rotation, right, caused by the vector field. Okay, there's going to be rotation, and depends on the location. The rotation speed or the angular speed at a different location will be different. Depends on the y value. Okay, yeah. And this is sometimes we call it a shear flow. Okay, in fluid mechanics, shear flow. Basically, in the fluid flow, there are different levels, different shear, different layers, and each layer has a different speed. And that's what we call the shear, right? It's like you have a shear force in the mechanics of material, okay? Yeah. And this vector field, we show that in the previous, this is basically a vector field basically describing the rotation of a rigid body. So if you put a point over here anywhere in the field, so that point will rotate about the z-axis at a constant angular speed. In this particular case, angular speed is omega equal to 1, right? And when you calculate the del cross that vector field, we get 2k hat here. So basically what it means is, if I'm looking at this point, or this point, or this point, so it doesn't matter where you look at it, the del cross V is always 2k hat. So which means what? Which means the microscopic circulation at any one of the points inside the field is the same. They all have 2k hat. And the magnitude is all 2. So if you place yourself over here, or yourself over here, or here, you're going to rotate about your center axis. Everywhere, doesn't matter where you look at it, the magnitude is always 2. Does that make sense? So here is an animation here to see if I can So you can see this vector field, this one here, that's the vector field I just shown over there, right? If you place a sphere inside this vector field, so guess what? It's going to rotate about this center axis with an angular speed omega equal to 1 if that's the field we draw there. But if you fix this thing here, fix the axis of fix this location. So basically, if you look at this one here, so don't let it rotate, assuming it's not rotating about the z-axis. Guess what? You will see this self-rotation about its own axis, center axis. So this rotation is described by which quantity? This rotation. That's the curl. Okay? The curl F gives you this rotation here. That make sense? Yeah. So here is another Wikipedia here. So you can see there are two different fluid flow here. Okay, the first fluid flow representing is basically it's a rigid body rotation. So if you toss a ball into it, you see there is the axis, basically center axis here. So the ball will rotate about that axis. So if you watch that the white line there, if you watch carefully the white line, does the white line, assuming it's not rotating about the z-axis, that white line segment is also rotating about what? About itself. So, but if you watch the second one here, the ball is rotating around the z-axis just like the first one. But the white line segment there, if you watch carefully, there's no rotation about its center. It's always doing what? Like this. Can you see that, right? So, which one has a curl equal to 0? The top one or the second one? The second one. Okay? So the second one has a curl or del cross F equal to 0. And this is what we call an irrotational vortex. Okay? And the first one is a rigid body vortex, basically. And we call that uniform, basically. Uniform, just like the one I showed you here. Why is it uniform? Because it doesn't matter where you look at it, it's always two key heads. That's why it's called a uniform field. All right? Yeah. So anyway, as I said, even if you don't want to accept, what the explanation in here, you can still calculate, do the computation, del cross F easily, right? Yeah. Okay. So this is another example I give you. This is a whirlpool here. Basically, as we mentioned, you find that del V equal to 0. Right, at any point other than origin. Okay. Okay. Yeah. So the other topic that we went over is the Green's theorem. So in Green's theorem, I'll write down the formula again. So the formula is this. Okay, so F Green's theorem dealing with, so there's a lot of assumptions. A lot of time you gotta be clear about where the theorem is applicable. So Green's theorem is applicable to vector fields, okay, in the planar, in xy plane. There's no z component, right? There's no z. The function is not a function of z. And it's used when this vector field f is not a conservative. Okay, I'll show you a little bit here. So f is not conservative. Because f is a conservative, you actually don't need to do anything, basically. It's just a 0, right? And this C here is a closed curve. Okay? So that's how you make use of the Green theorem. Essentially, the idea is you don't want to calculate this left side, and then you calculate you basically to get the answer by evaluating the double integral. Right? Instead of evaluating a line integral here. Okay? Yeah. Now, if I look at this formula, okay, with a second look at it here, what is this integrand at here? This integrand. If I go back to the first review part, what is del cross F when you have a planar field? Which is what? Which is this, right? So what we have at here in terms of this Green theorem, the integrand, this portion, which is basically the what? The magnitude of that del cross F. See this portion? That's the magnitude of del cross F, isn't it, right? So I can rewrite this portion as del cross F. Okay, that's the magnitude dot k hat. Okay, dot k hat. Does that make sense? So if you look at this del cross F, this is a del cross F. When you use this dot k hat, what do you get? You get its magnitude. Okay? Yeah. Okay, so now if you look at this big bracket here, basically this is what you are integrating. You're integrating this quantity over where? Over this region R. So if I draw the relationship at here, if I draw the relationship, so where's my C? So let's see, I'll write it down here, CF ds. Okay, so this is a C curve at here. And where's the R? R is enclosed, the region enclosed by curve C. Okay? Yeah. Then what is this del cross F dot k hat? Have we just gone through this? What's the del F dot k hat? Definition. Del F dot n hat. If you change the n to k, that's del F dot k hat. Was that right? What does this quantity mean again? It's the circulation density at a certain point. Basically this, remember this one here, right? This gives you the microscopic idea. And what we can imagine is, so for this particular one here, inside this bracket, what this represents? This represents, as we said, represents as a microscopic circulation, the kind of a quantity, microscopic circulation. So it's like this, right? At this location, there is a kind of a circulation going on. It's like at that particular location in the river, there is a little vortex. Okay? And at another location, there's another one. And each one of them is described by this guy. Okay? By this one. By this guy here. And this double integral, what this double integral is doing is what? What's the integral? Integral is basically means sum. You're adding all the quantity together. So what are you adding together? You're basically adding all of this microscopic circulation all together, which give us, what does that give us? The big circulation around the curve C. Right? Excellent. Yeah. Does that make sense? So I guess, you know, what I'm trying to do at here, trying to give you a venue to understand this green theorem here, right? But otherwise, you know, you write this formula 10 times, it's yours. Okay? Yeah. Okay? So that's green theorem. And then we started the concept called flux. Okay? So flux, we started concept basically saying is there you have a vector field. And you don't see the vector field. The vector field is everywhere in the 3D space. So in order to describe this vector field, and often in time we use this so-called streamline to describe the vector field. So it's as if you have a number of lines going inside this 3D space, right? Then the flux basically is if you have a surface, okay, inside this vector field, then how much of this quantity represented by the vector field will go through this surface in unit time? So that's basically flux, right? Yeah. So now you can see, as I mentioned in the lecture, the amount of quantity going through the surface depends on three things. One is the strength of the field. So if you look at this first portion here, okay, this first portion, the strength of the field generally can be represented through these streamlines. If you look at the margin or the space between the lines, if it's more dense, right, then you have a basically stronger field than the one with the less margin or space. Okay? So apparently, given the same surface, there's much more flux, right, for this one here. If you orient your surface differently, even if the strength is the same, because you can see the spacing between the two fields are the same, the spacing. But this is oriented different from this one, and there's less flux compared to this one, right? Less quantity passing through the surface than this one. If you have a size of the surface different, it's the same thing, right? Same idea. So that's basically what we mentioned here. So three quantities, right? Basically, flux, it depends on the vector field F, and also depends on orientation. Okay, orientation between F and the surface. Okay. So and then also depends on the size of the surface. Okay. So that's what we're going to basically try to come up with a certain formula, right, to evaluate this quantity flux. And that formula we're going to come up with is the so-called surface integral. All right? Yeah. Any questions? Good. So this is what we're going to talk about today, surface integral. For flux. Okay, so basically, the calculation, the results of the surface calculation of the surface integral give us the flux. Okay, so let's start from a simple one in here. If I have a tube and then there's water flowing inside the tube with a constant speed v, and the tube at here has an area, let's say A1, okay, area A1. So then the question is, what's the rate of the flow of the fluid, okay, basically passing through this cross section A1 at here. And assuming that the fluid has constant mass density, okay, constant mass density rho, okay, yeah. Then V, let's say the magnitude of V give us just a speed, okay, yeah. So how much of the fluid will pass through this cross section A1 in unit time, or what's the rate of the fluid passing through A1? So let's say W is the rate of the flow, okay, across A1. So W equal to what? The density times A times V1 times A1 times V. Okay, so W at here is this rate of flow, okay, across A1. Okay, yeah. That makes sense? Yeah? Yeah. So basically, if you can, in terms of unit-wise, if the density is kilogram per cubic meter, velocity is meter per second, and the area is what? Meter square. Then the rate of flow W give us the unit, which is kilogram per second, right? So you have this amount of fluid will pass the cross section per second. Okay, that's the rate of fluid. Okay? Yeah. So this is the cross section A1 perpendicular to the flow of the fluid. Now, what if the V1? So let's just change this just slightly. If the V1, so I'll look at the cross section only. Okay? Just look at the cross section. If this is a cross section, let's call it A2. Okay, A2. And the V, still the same V as before. And suppose that this is A1, there's an angle theta between. Then now, what is the rate of flow across the cross section A2? Right? Okay, so same idea. So to do this, let's say I have a normal vector, okay, n hat, that's perpendicular to this A2, okay, the surface area A2. Okay. So the amount of fluid or flow passing through the A2, let's use the W. This is W1 here. Let's use W2 for this one here. Okay, yeah. It's going to be rho times A2 times V, but not the V anymore. It's going to be what? The projection of the V in the direction of n hat, right? N hat. So in terms of the geometry, it's basically times cosine theta. Okay. So if I use a dot product, this is going to be rho V dot, which one? N hat, right? Rho V dot N hat. Then times A2. Okay? Right. That's the rate of flow across the section area A2. Does that make sense? Okay? Yeah.
I don't really understand. Why do we have to project the velocity in that direction?
Well, we're talking about the perpendicular amount of fluid. Okay, the perpendicular, the fluid perpendicular to the area A2. So you have this area here. You know, what's going through that area in the perpendicular direction, basically, right? That's the amount of quantity that we're looking for. Yeah. So now here comes the generic now, right? So this is a cross section like this. So what if I have a generic situation here? So generically basically means, let's see if I have in general. If my surface, if the surface is not regular, maybe I have a surface, you know, basically like this in the 3D field. Okay? Yeah. But no matter what kind of surface that you have, guess what? At any one of the points on the surface, you can always draw, what can we draw? N hat, right? We can always draw an N hat at a location just like this N hat. Okay? Just like this N hat. And now maybe you have a vector field. Who knows, right? You know, spread it inside this 3D space. So the same question, what's the rate of flow, or what's the flux, basically, passing through this surface S at here? That make sense? Yeah. So again, we're going to resort to the concept of approximation first, and then resort to the limit. So we'll end up with the integral, basically. Okay? Yeah. So here's what happens. So what we can do is, let's take a very small patch, right? Let's take a very small patch at this location. So for this one small patch, maybe I'll call it basically delta A vector, right? Delta A vector. So what is this delta A vector? This delta A vector has a magnitude of area delta A and an orientation given by n hat. That make sense? Yeah. And at that particular location, you may have a vector field f maybe going this way. Who knows, right? Maybe going this way. Okay? Yeah. So, and then this is basically the next diagram. I'll show you where the formula is derived here now. Okay, so are you okay with this diagram now? I'll just move it down a little bit here. Yeah. Okay. So this is what I draw here. This is a delta A, and this is n hat. And because let's assuming this is small patch, then assume the vector field within the small patch is constant. Okay, is a constant. So, and the vector field is constant like this. So then, within a unit time, it's like there's a blob of fluid passing through that surface here. Can you imagine that, right? In unit time, there's something, a bubble, you know, of things going through it. And here we're using a so-called parallelepiped, right, to represent the blob of fluid passing through this area using this volume, basically. So what's the volume of this box then? First lecture. Remember the first lecture we had a volume of parallelepiped. But anyway, volume is always equal to what? The area of the base times the height. Okay? So what is the area of the base? Delta A. Now what's the height then? Exactly. So F dot n hat. So I'll arrange this slightly here. So F dot n hat times delta A. That's the volume of the parallelepiped, and that's the blob of fluid passing through that small cross section delta A in unit time. Okay? But we are looking for is what? Is the total quantity passing through the whole surface S. So then basically the total is you add all of this across the whole surface. So the total sum becomes an integral. Integrating across the whole surface area, integrate what? Basically, or add what? Add this quantity here. Okay? That's surface integral formula. And this is basically, we call that flux. Okay? So we call it flux. Is that clear? So first of all, let's revisit this. You know, each one of the quantity, what do they represent here? Okay? Yeah. F is the vector field. And n hat, what's n hat? Direction or direction perpendicular to what? To the surface. Delta A is a small patch. So I guess I don't use a delta A anymore. I should use what? dA, right? So use D. So dA is a small patch. So then you probably would ask is, why do you write two integrals? Why not three integrals? Because this dA at here, right? So, you know, in the xy plane, what's dA? dx dy. And if you integrate, you just need two integrals, right? And chances are the delta A or the dA may not be necessarily or beautifully in the xy plane. Maybe it's in a 3D space. But however, you know, you generally you just need two variables to calculate the area of that patch, right? So that basically means we only need two integrals or two integration operation to evaluate this double integral, to evaluate the surface integral. All right? Yeah. So now that brings this natural question now, right? If I only need two variables to evaluate this double integral, then what kind of two variable should I use then, right? First of all, let's do a little recall here or review here. If I'm using Cartesian coordinate, what variable do we use? X, Y, Z. If I'm going to use a cylindrical in 3D, what are the three variables? R, theta, Z. If it's spherical, rho, phi, theta. So in 3D space, you need three variables to describe a location, right? But for the surface integral here, as I said, you only need two integrals, or you only need two variables. So the question basically here is, in terms of dA, what are the two variables shall we use, essentially? Okay? Yeah, that's basically, if we can identify that, we'll be able to carry out this integral. You see what I'm saying? So for example, maybe my dA, if I use the spherical, and I choose d phi, d theta, so then I gotta have a constant in here. And that's what's gonna be used for the integration, right? If I'm gonna use a Cartesian, as we said, maybe I'm gonna use a dx, dy. So apparently it's gonna be 1 if the small patch is in the xy plane, okay? Yeah. So the next step is basically, let's figure out this formula, okay, according to different cases. Okay, some cases are easier, some cases a little bit more difficult, right? Yeah. So let's look at the first case. Let's look at actually the first case. Maybe it's not that easier case, but it's a pretty special case. Let's look at spherical surface. What if the surface that you are asking for, to evaluate the flux is a spherical? Basically, it's a part of the sphere. Then how do we deal with the situation? All right? Yeah. So here is a drawing. So here's the drawing I'll use to illustrate the situation in here. It took me a while to draw this thing a couple years back. So here is delta A on the small patch, okay? On the small patch. So you don't need to draw this, okay? But I'll just illustrate this. Actually, when I give you the results, and you'll see you actually see this already, all right? So basically, how do I express this delta A? Okay, the delta A here. I'll basically approximate this delta A using a box, okay? Using a box. So the area delta A is this side times the other side, right? Yeah. And because it's on the spherical surface, so the delta A is created using the latitude line and longitude line, right? Yeah. So basically, we have the phi, we have a theta, we have the A. Now, what is A then? A is the radius of the sphere. So here you got to be very careful. Basically, what's known, what's unknown. Because we're talking about is the spherical surface. So the known quantity, basically, if the spherical surface is determined, then the radius A is a constant, right? So A is a constant here. So now you can see now, the red side is A times delta phi. And the blue side here is A times sine phi delta theta. Then the delta A at here is basically the two quantity times each other. You get A squared sine phi delta phi delta theta. Okay? Yeah. That's delta A. Then what is dA then? Does that make sense? That's dA. Okay? Now, if you recall that in triple integral using spherical coordinates, the dV, transformation of dV in Cartesian into the spherical, what's the formula? Equal to what? This is what? Rho square sine phi. So if you compare these two, over there is a d volume, over here is a d area. So the rho basically changed to a, to a constant, and you don't have a rho anymore because rho is constant, so there's no d rho, there's no integration here. See the connection here, right? Yeah. Okay? So this is a dA when you have a spherical coordinate, when you have a spherical surface, okay, like this. Okay. Bottom line is, if I go back to my flux formula, okay, if I go back to my flux formula here, here's my flux formula. I am going to fill up the space that is here, the unknowns, and I got the information for the dA now, right? For the dA. Okay, so let me write down here. Okay, so this is the formula for flux. Okay, this is formula for the flux. And this is a dA. So now the question is, what is n hat? Remember what the definition of n hat is. N hat is a unit normal vector to surface. Now the surface is a sphere. How do I get these n hats then? If I pick a point on the surface, okay, if I pick a point on the surface, what's the coordinate? The coordinate is x, y, z. And where would you draw the n hat? You draw it perpendicular, right? And if you extend that vector, where is that going to vector go? To the origin. So now, can you create an n hat for me? What is it? A hat. A hat. What a hat? You mean a hat like this? Well, a is not a vector though. A is a radius. So let's say this is the radius here. Ah. So n hat equal 1 over a and what?
X, Y, Z.
Exactly. Why is that? So you see what I just said here. You know the vector. You know a vector. Basically, which vector is perpendicular to the surface? From here to here, right? That vector. And what's this vector? From here to here, to the point. For the point P. What's the vector? OP equal x, y, z. What's n hat? What's the magnitude of OP? That make sense? Yeah. Now that's your n hat, right? Yeah. So n hat is known, dA is known. There we go. We have our surface integral. Now if I plug in into the formula, so the surface integral is the vector field F, whichever it is, right? So, but now you gotta also be careful now. Before we do that, let's see here, right? So let's say we fill out another one here. The vector field F is probably MNP, okay? And M is a function of x, y, z. So what do we do with this x, y, z here? You can mix x, y, z with what? With Where's my rho A? Where's my D with the phi and the theta, right? So you have to, put everything into one set of variables. In other words, we have to change this x, y, z here into this phi and theta. How do I do that? Spherical coordinates. What's the conversion between the spherical coordinate and x, y, z? X equal to rho square sine, rho square sine phi cosine theta. Y equal to, but don't write it yet, okay? It's not a rho. It should be what? This is the coordinate change between Cartesian and spherical. Do you remember that? But now we're talking about, just give me a second. We're talking about the spherical surface of a radius of A. So instead of a rho method here, we actually just have to use, okay? Yeah. So now imagine this. If you plug this xyz with this, there's no xyz anymore. There's only phi and theta. Does that make sense? Yeah. So in the end, your surface integral is a vector function in terms of phi and theta after you do the substitution, dot this n hat and the dA, and dA as we just find it, it's a squared sine phi and d phi and d theta. Okay? D phi, d theta. Yeah, that's right. Yeah. And what is n hat? N hat is this guy here. Replace the x, y, z with whatever here. Okay? Yeah, same thing.
How do you get 1 over A?
Given point P here, the perpendicular vector to the surface is OP. Is that right? N hat is a unit vector, so normalize the OP with its magnitude. So OP is x, y, z. You normalize that with its magnitude. What's the magnitude? It's A, right? It's the radius. So this is where the N hat is come from. Is that good? Yeah. Okay. So the next question is, how do I get the limit for the phi and theta? You're doing integral, right? You're going to have to basically find the limits, everything in here, like this. That make sense, right? Yeah. So if this is a surface, if this is a, maybe half sphere, maybe quarter, who knows, right? Yeah. How do I find phi and theta? Have we done that? It's the same way as you did for the triple integral. Okay? The same way as you did in triple integral. If it's a whole sphere, if this is a whole sphere here, what's the phi range? 0 to pi. And theta is 0 to 2 pi, right? Yeah. So when you do triple integral, the idea is to sweep through the whole region. When you do surface integral, the idea is to do what? To sweep through the whole surface. Okay? Yeah. So let's take an example here, okay? Here's my simple vector field, f equal to 0, 0, z. And we have a sphere centered around the origin, okay? And with the radius of A. So sphere radius is A here. Then what is the flux across this surface, or the spherical surface that is here? Okay, so this is a simple question. All right, so let's fill in the blanks that are here. So what is F? Maybe before you do this, we can do this kind of separately here, right? So F dot n hat. What does F dot n hat give us? F is 0, 0, z. And n hat, as we just derived, is 1 over the radius, x, y, z. So overall, this gives us 1 over a z squared. Okay. And what is the z then? We replace the z with what? A cosine phi. So 1 over a cosine phi squared. Okay. So a little simplification give you a times cosine phi squared. Okay. And dA, as we derived, equal to a squared sine phi d phi d theta. Right? That's it. So now let's plug in and find the limits of a phi and the theta. So plug in this quantity here, it's a cosine square phi. Plug in the dA quantity, a squared sine phi d phi d theta. It's a whole sphere, as we just said. Phi is between 0 to pi and 0 to 2 pi for theta. Right? Yeah. That's it. And this is not too bad in an integral here. You can use a simple substitution to do this, right? You can let u equal to what? To cosine phi. Okay, and you can try it. Okay, yeah, yeah.
So I'm a little confused as to why we're using the z coordinates. I thought with dA we're just going to use x, y, right? But we're still using x, y, and z, like we would if we're trying to find volume.
You're not finding volume here. Okay. This x, y, z is naturally there because of the vector field. Okay? Yeah. But the surface integral constrain you to where? To the surface. And in this particular case, we're considering special case, it's a spherical surface. Okay? So in this particular case, the n hat, the dA, because of this spherical surface, is what we find out to be n hat is this, and dA is this. Because this is spherical surface, right? And you're integrating over this spherical surface. The x, y, z coordinates on the spherical surface is described or can be transformed to phi theta using these three formulas. So that's why you can replace all the x, y, z with these three formulas there. No? Yeah. So yeah, you know, it's okay. You know, you need a little bit, basically digesting it. Yeah. Anyhow, that's the spherical surface. Okay. Yeah. Any questions? So now let's take a look at the second case. What if I have a plane? Okay, it's a plane surface. It's probably a pretty simple one. It's just a z equal to a. So that's a plane parallel to xy, right? To xy here, okay? And if this is the case, so here's a plane, and this is A at here. Then how do we evaluate that surface integral? Well, no, you don't need cylindrical coordinates. A little bit too much for cylindrical, right? But let's basically try to fill in the blanks at here. What is n hat in this particular case? Z hat? What do we call that? K hat. Close. What's dA then? How do I represent a small patch? dx dy. That's it, right? Now this is probably easy to accept because there's no other variables. So it's just original x and y, right? Then what would be the surface integral look like now? F is MNP, okay? So MNP. N hat is K hat, which is 0, 0, 1. dA, dx, dy. So overall, this formula become this P times 1 is P. So this is Pxy z and dxy dz. Okay, so here's the trick now. What do I do with the z? No, z equal to a, because this is your surface, z equal to a here. So that has to be changed to a. Okay? Yeah. And how do we find the limit for x and y? And basically, let's say maybe the projection of the surface is this much region. So basically, you find your x and y same as a double integral, right? Same as double integral. So look at what the shadow looks like, basically. Maybe it's a rectangle. Maybe it's a circle. Who knows, right? Yeah. Come again? Oh yes, it would be. But that in particular case, you're not going to give a plane with infinite boundaries, right? You would give maybe, hey, look, here's a disk parallel to the xy plane. Here's a rectangle parallel to the xy plane, that kind of case. Yeah. Okay, so then you can expand the knowledge here. What if I have a plane? Basically, what if I have a plane parallel to xy plane? What if a surface parallel to xz plane? And what would be the formula look like for the surface integral? Okay, so in this particular case, you can imagine. So if that's the case, what does n hat? What would be the n hat then? If it's a surface parallel to the xz, this is x, this is z. J hat. That's right. Okay. And what about the dA? dx dz. Okay. Okay. So here comes the tricky part here. Okay. Yeah, you got to be careful because at the end of the last lecture, you will probably sometime will come into this one here. Now I said n hat is k hat. Can you give me another n hat? Negative k hat, right? Yeah. So you do have two options, basically, right? You do have two options. So the two options actually makes a lot of difference. See, one people will ask you is this: how much of this quantity will pass this surface in the positive z direction? And the other guy, how much of the quantity will pass in the negative direction? So, of course, you can see all the opposite value here, right? But when you evaluate, when you apply this formula, the n hat should be conform to the direction you're referring to. Does that make sense? Yeah. In a lot of time, when we have a closed surface, we refer the outward direction as the positive direction. But if it's not closed, we don't have a convention here. All right? Yeah. So just remember this. We'll come back to this concept. Okay? Yeah. So technically, you could have a positive and negative G hat here too, right? Okay. So I'm gonna quickly go over one example, then we'll jump to the next type of surface. F equal to -1, 2, 3. The surface S is Z equal to 0, bounded by this range. Okay, by this range. Okay, and I want the direction is K hat. Okay, direction is K hat. So basically, what do we mean? Basically means we need the flux in the positive Z axis. Okay? F is a constant field. So -1, 2, 3. Dot the N hat. N hat is K hat. So 0, 0, 1. Okay? 0, 0, 1. dA is dx, dy. Because this is the plane parallel to the zx, to the xy plane. Actually, it's the xy plane, right? Xy plane. And limit for the x and y is, okay, like this. So what are we looking at? Basically, we're looking at is the basically it's this. This is the surface, right? Okay, this is the surface in xy plane. And you have a constant vector field. Okay, like this. So how much of that field goes through this patch, this rectangle, right, in unit time? So you can calculate this, and this is equal to 18. Okay. So all good? Yeah. So case number 3. So now you can see actually the surface integral is actually nothing new here, isn't it? What's new in terms of computation? If you know if you have this thing, everything here, if you know how to do a double integral, you know how to do a surface integral ultimately. Okay? So cylindrical surface. Okay? Cylindrical surface. Basically, we may have deal with is a cylinder kind of an object with a cylindrical surface centered around the 0, okay, or the z-axis. That's a cylindrical surface, all right? Yeah. And we wanted to evaluate the flux through this cylindrical surface. Okay? Yeah. Okay. So same idea, right? Same idea. Now, if you remember from the triple integral, how does the dv turn into the cylindrical coordinate? It's r dr. So r dr and dz at d theta, right? Yeah. But that's basically you're trying to cover, to sweep through the whole region, the cylindrical region. But in this particular case, we only interested is what? Is where? Is the surface. So which means if you have a cylinder, basically, how do you describe cylinder first of all? X squared plus y squared equal to a squared. What is it? It's a circle, right? But in 3D space, this is a cylinder. Or r equal to A. That's a cylinder. Okay? So you're only interested in the surface of the cylinder. So the R here is not going to be part of the integration, which means that dA will be, what would that be dA? You're looking for a small patch on the surface of the cylinder. A times dz d theta. Because the R is gone, right? dr is gone. And R is turning into A. Okay? If you need a better derivation, you can look at the lecture notes by calculating the rectangular basically area for the dA, delta A, and then you get this. Okay? Yeah. So that's dA. Then what is n hat then? What's n hat? So n hat, as we know, is a vector normal to the surface. So if you pick a point here, the n hat should be perpendicular to the surface. If you pick a point at here, the n hat should be perpendicular to the surface. So what's the nature of this n hat? If I extend this n hat, it should. If I extend this n hat, it should. Does that make sense, right? So let's say this is a P point. What is the vector perpendicular to this point P, or to the surface? OP is perpendicular. And n hat should be normalized. And what is the OP vector then? If I look in at this location, x, y, but we're looking for is 3D. So if I see, if I'm going from here up to this location, going straight up here, okay, straight up. So the difference between this P and a Q is what? So the P is x, y, 0. But the Q is what? X, y, oh, not A, straight up to here. Z, right? Z. But is there any difference though for the unit normal vector at the P and Q location? Not really, right? And they are all what? They are actually all basically extended, just move the OP up to here. It's the same vector, right? So the vector here is basically x, y, z, 0 over the magnitude of OP. And magnitude of OP is A. So A in hat is 1 over A x, y, 0. All right? So you have a dA, you have the n hat, and now you basically pretty much solve everything, but we still have a mixture of x, y, and z theta. So what we need to do is what? This x will have to be changed. So the x will be changed to, remember, in cylindrical coordinate, x equal to, in cylindrical coordinates, what's x? R times cosine theta. But this is the surface only, so the r will be changed to A. And y equal to A sine theta. And the z equal to z. Right? Z equal to z. Okay? So then let's summarize. The surface integral for cylindrical one is f dot n hat dA. That's a surface integral. And how do we do with that? So basically f is mnp. Okay? And n hat is 1 over A x, y, 0. dA is A times dz d theta. Okay? A times dz d theta. So let's simplify this a little bit here. This dot product, because there's a 0 here. So essentially that gives us m times x, n times y. And this 1 over a will cancel this a at here. You end up with a dz d theta. Okay? And over the surface S. Okay, surface S. How do we find the limits for z and the theta then? Same way as the triple integral, the dr dz, the same way as you do. Okay? How do we find the z? We draw a line, right? Through this cylinder, from the bottom and top. Theta, we need to rotate to find the limits bound to this surface. Okay? Yeah. Okay. Yeah.
You change those x and y to.
Yes, you will have to change this x, y, z here using the 3 things here. Okay? So let me give you an example, okay? F vector field is x, z, negative y. Okay? X, z, negative y. And surface is a cylinder. Okay? So it's basically a cylinder with a radius of 1 centered about the z-axis. And z is between 0 and 1. Okay? And what is the surface integral? Okay, so let's do this according to the formula that we just derived here. So in this particular case, a equal to 1. Okay? Then what is n hat? So x, y, 0. Here's n hat. Okay? And what is the dA then, right? So we can manipulate now. Okay. All right. So F is x, z, negative y. X, z, negative y. Dot this n hat x, y, 0. Okay. X, y, 0. And dA equal to dA equal to a dz d theta. So dz d theta because a is 1. Okay? Yeah. Over this is surface S. Alright, so now for this one here, dot product give us x squared plus zy. And dz d theta. Okay? So, replace the x. Replace x with a cosine theta. Replace y with a sine theta. Replace the z with z. So don't touch z though, right? You don't need to touch that. What's x? A times cosine theta. A is 1, so cosine theta squared. Y is a times sine theta. Okay? Yeah, that's the replacement. And the limit. Limit for the z. What does this thing look like? Yeah, 0 to 1, and theta goes from 0 to pi. Right? Because it's a cylinder. Okay, like this, right? It's a cylindrical surface. Okay, so I don't think this is a tricky integral either, and you can. I'll just one more step at here. Okay, so this is the integral here, right? This integral. This 1 over 2 sine theta is pretty easy to do. And this cosine theta squared. If you recall, actually, the formula sheet, you have this formula. Cosine theta squared equal. Okay, you can use this trig identity. Yeah.
Like, let's say on a final, we have that.
You have this.
Okay.
It's already included in the formula sheet. The formula sheet is posted. I forgot to bring it here. Actually, I'll print it out. I'll bring it here next Monday. Yeah.
Will you specify which method to use?
Sorry?
Will you specify which case?
I don't need to. If you see a cylindrical surface, use this. If you see a spherical surface, chances you're going to use a spherical surface. Right? Yeah. So, any questions? So we have one more case, which is basically not so special case. I'm not going to cover today now. What if I have a generic surface z equal to f of xy? Okay? And then that's basically about it for surface integral. Okay? Yeah. Any questions? All good?